Welcome to the second week of Audio Basics. We talked a little bit about what sound is in terms of being a longitudinal wave, wavelength and amplitude and periodic sound pressure moving in the air. But this week we're going to get a little deeper into various types of sound generation. Everybody in here is familiar with all different kinds of instruments that create sound, and so we're going to start talking about the principles of sound. Sound waves, commonly produced by vibration, strings, drums, wind instruments, speakers, jackhammers, anything that creates a disturbance in the air will create a sound. There's three basic types of formations of sound waves. Mostly we'll be dealing with periodic sounds, meaning that it's a repeating cyclical kind of a sound wave. It's a periodic sound that is repetitive. Impulse, on the other hand, is a different type of sound. It's a disturbance in the air that actually traverses time. So it's not periodic. It's like a cymbal crash. It's not a periodic sound at all. Third is noise. Noise is all frequencies at equal amplitude. We all experience noise in our daily lives without even realizing it. We just sort of tune it out. If we're all very quiet in here, we'll hear very quiet undertow of noise of whatever's going on outside. It's all of this cumulative ambience that creates sort of a noise floor. So that's the three basic types of sound. Sound waves. So some sound waves are periodic and can change over time but repeat. The frequency of repetition will determine the fundamental frequency of the sound, and impulses are shorter, non-repeating sounds, drums, cymbals, hammers. Some sound waves are a combination of impulses and repeating waveforms. That's kind of important to understand, is that these three categories of sounds aren't isolated between each other. They combine together, but they can be broken down into those categories or classes of sound. Sound noise floor is not to be confused with electronic noise floor. There's an electronic noise floor in every electronic circuit. That's just the basic undertow of current flowing through the components. And we'll discuss more about electronics in a later class, but I wanted to make that distinction because when you hear about a noise floor in a piece of electronic gear, it's different than a sound noise floor. All complex waveforms can be a sum of sine waves at different amplitudes and frequencies. Most musical sounds are the sum of sound waves at fundamental frequency and harmonic frequencies. I'll explain what those two terms mean as we go along in the next couple cards. Most sounds that you hear are more complex than the simple sine wave. We're going to discuss a lot more about that complex waveform. Here's an example. So these sine waves added together, these three different sine waves, this would be the lowest frequency and the largest in amplitude, the next highest in frequency, quieter in amplitude, and much higher frequency at lower amplitude, combined to create the sum of these waves, which ends up being a bit of a sawtooth wave. So if you look at the sawtooth wave as a more complex version of a sine wave, you can see that the sawtooth wave can be created by adding together sine waves. It's almost like thinking of it as a brick wall, and each brick in the wall is fundamentally important to creating the wall. So the complex sound wave would be compared to a brick wall, and the individual frequencies would be compared to each brick in the wall. No reference to Pink Floyd. I'll lay off the jokes. I know we're getting technical here. Okay, so harmonic series is a series of multiples of the fundamental frequency, which is very interesting because your fundamental frequency is your first frequency in a complex sound, and the harmonics above it, the added sine waves that go into making this complex wave, are multiples of the fundamental frequency. The balance of how loud they are of the particular harmonics creates the timbre of a sound. Has anybody ever wondered why a female voice singing middle C and a piano playing middle C and a saxophone playing middle C, why they all sound different? It's the same pitch, and why do they all sound different? They have a different timbre. Timbre is created by these frequencies that are above the fundamental frequency. Fundamental frequency handles pitch information, and the timbre, or the other frequencies in the complex sound, create the character of the sound. So if I were to sing middle C and you were to sing middle C, we'd sound different. We'd sound different because of the way our voice resonates in our vocal cords, in our sinus cavities, all of that stuff, and each physical structure is a little different. So it creates a little different harmonic structure. Let's go back a bit and talk about who discovered the principle that a complex wave could be broken into fundamental elements? Mr. Fourier. He came up with a mathematical formula that proved this. He was dealing mostly with heat transfer variations, and it has nothing to do with sound, but it has everything to do with sound. It's a very far-reaching theorem that he came up with. It's one of the fundamental things that we use to understand sound. Complex waveform will equal a sum of various frequencies at different amplitudes, different sine waves. Complex wave is, in addition, an infinite series. These sine waves, they go on infinitely to create an actual harmonic structure. So you've got a fundamental frequency and you've got harmonics or overtones. But that's the basic principle, that a complex wave could be created out of fundamental sine waves added together. So let's just look at a simple square wave. So here's the sine wave that's closest to the more complex square wave. That's the fundamental frequency of the square wave. Then if we add the first harmonic, the first frequency above the fundamental, it ends up looking like this, which starting to look a little more square. Adding the third harmonic, adding the fourth harmonic, it becomes more and more like the square wave. And actually the fundamental frequency and the harmonics, all of them, have different properties, and we'll discuss what they are in terms of what you hear and how you hear it. So you can call them overtones, and those overtones, because it's over the first tone, which is the fundamental, creates the timbre, which is the quality of sound, so you can identify, oh, this is a human being singing and this is a saxophone playing the same note. So it gives you the quality of the sound and tells you exactly what you're hearing. So what I was doing here was trying to give you sort of the layman's point of view, that you go, okay, I'm starting to buy the fact that maybe this does work, that if you add together sine waves, you could create a square wave. But the theory is you could create any complex wave, absolutely any complex wave. Every complex sound has a fundamental frequency and overtones or harmonics above the fundamental that create the complex wave. When we EQ, when we compress, when we do manipulate these sounds in our recording devices, we're actually affecting various frequencies. And so I'm trying to give you this frequency domain example of a sound, meaning that your sound, whatever complex sound it is, whether it's a piano note or a guitar, is a complex wave that can be broken into various fundamental and harmonic frequencies. So it's a combination of frequencies added together. The fundamental and the harmonics actually have various properties that we as humans can hear and identify. So the first frequency is called the fundamental frequency. It's the loudest frequency, and it carries pitch information. So that's how we hear what the pitch is. If we didn't have a fundamental frequency in a sound, we would be less able to identify pitch. The higher frequencies above the fundamental are called the harmonics or overtones, and they create the character of the sound. And they're decreasing in amplitude. So the two things that's important to remember here, the fundamental frequency is the loudest and carries pitch information. The higher frequencies above that are called harmonics or harmonic structure, because there's a structure of frequencies, and they're decreasing in amplitude as you go higher in the spectrum and higher in frequency, and they carry the quality of the sound. They tell us what the sound is.